Alright, so in this video we're going to derive the variance of our least squares estimator B using matrices. Alright, so let's start by recalling what our linear regression model looks like. So we have y, which is a n by 1 vector of all of our y's, equals x, which is our design matrix, times beta, which is the vector of our model parameters, plus epsilon, which is the vector of our model error terms, right? And there's the assumption that the variance of our model error terms equals sigma squared times I, where I is our index matrix, that is n by n, right? So let me go ahead and write that down. So n by n index matrix. So basically what does this look like? It has sigma squares in the diagonal, right? Remember, what is the index matrix? It's 1's the diagonal and then 0's everywhere else. So when you multiply it by sigma, you're going to have by sigma squared, you're going to have sigma squares in the diagonal and then 0's everywhere else. All right, so this is our variance of our model error term, right? And because x is non-random, this basically yields the result that the variance of y is also sigma squared times I, right? So that directly follows from the variance of the model error term being sigma times I. As a result, the variance of y is sigma times I. Okay, so our least squares estimator is B, right? And that equals x transpose x inverse times x transpose y, right? And the goal here is we want to know, well, what's the variance of B? That's going to be equal to the variance of x transpose x inverse times x transpose y, okay? And in order to kind of bring this variance in here, we need to remember something about variance. So if you have variance of a matrix times a vector like this, and where A is not random, right? So it's like a constant, and basically all these guys are constants because X is not random, only Y is random. So here A is just some non-random matrix, Y is random. This equals A times the variance of Y times A transpose. Okay, so let's use that here. So we're going to have x transpose x inverse times x transpose, okay, times the variance of y times x transpose x inverse times x transpose, and all of this needs to be transposed. Okay, so let me go ahead and write that. X transpose x inverse times x transpose. We know what the variance of y is. It's sigma squared times I. Okay, and let's go ahead and bring this transpose in. So when we have a product, so we need to reverse the order of that product. Okay, so I'm going to have x transpose transpose, okay, times x transpose inverse transpose, right? So basically what I've done between these two steps is say if this were A and this guy is B, right? So if you have A times B transpose, this is the same thing as B transpose times A transpose, right? So that's basically what I've done here. So I have x transpose x inverse times x transpose. Now this guy is a constant, so actually let me go ahead and erase this. Let me pull that constant out front. Okay, the index matrix, it's not really needed there, so I can just go ahead and not write it. Remember what the index matrix is just a bunch of ones, and then zeros on the off diagonals. Okay, so x transpose x is just x. So this piece here is just x, right? You transpose it twice, you're going to get back to the original matrix. All right, so let's talk about this guy for a second. We know that x transpose x is symmetric. So if x transpose x is symmetric, then x transpose x inverse is also symmetric, right? That's a property of matrices. If you have a symmetric matrix and then you invert it, you still have a symmetric matrix, okay? So if this guy is symmetric, then this guy is equal to its transpose, right? That's by definition of symmetry. So the transpose of the inverse is also equal to the inverse, right? So I have here the transpose of the inverse, which is going to be exactly the same as just the inverse. All right. Okay, so now let's look at what we have here. We have sigma squared times x transpose x inverse times x transpose x. So you have the same thing being multiplied by itself, right? Once it's inversed and one it is not inversed. So when you multiply that, you're going to get an index matrix. All right? So basically they cancel with each other. So you're left with sigma squared, right? This guy cancels with that guy, and you're left with this term out back. So x transpose x inverse. Right? So there you have it. This is our variance of our least squares estimator B, right? And of course, sigma squared, it's not known, right? So this guy is unknown. He's our model variance, right? So how do we estimate him? A lot of times we'll use the mean squared error, right, which is s squared, which is the sum of our model error terms, right? Which, remember, our model error terms are just our actual observed values minus the predicted values. So the sum of those guys squared divided by n minus 2, right? So an estimate of the variance of B, right, an estimate of it would be s squared times x transpose x inverse, okay?